Okay, so let's start now. So now we have two more problems related to heat exchangers, and inshallah this chapter of heat exchanger will be over. And along with this heat exchanger, your whole area of convection, your whole portion of convection is over. So it started from chapter number 6, which was introduction. Then you had the external flows, then you have the internal flows, then you have the free convection, then you have boiling and condensation. Finally, you end up in a combination of all these things in heat exchangers. And that's it. Once heat exchanger is done, convection portion is over. So your conduction is over, your convection is over. The remaining thing is radiation, which is not really as big as convection and conduction. So that's chapter number 12 and chapter number 13. Anyways, so let's continue. Let's with the problem that we have now. This is example 11.5. The condenser of a large steam power plant. So we have a large steam power plant. For that we have a condenser, and that condenser is a heat exchanger. For now you know that condensers are heat exchangers, in which steam is condensed to liquid water. I've assumed the condenser to be a shell and tube heat exchanger. Now a condenser is a shell and tube heat exchanger consisting of a single shell. So we have one shell and 30,000 tubes. So in that, this is a very huge shell. In that shell we have 30,000 tubes, each executing 2 passes. So basically we have 2 passes. So it's like this: 30,000 tubes enter into the shell and then take a U-turn and return back. Okay, so this is one pass, and then this is the second pass. Okay, the tubes are of thin wall construction with diameter 25 millimeter. You have gone through problems of thin wall. Okay, diameter 25 millimeter, and steam condenses on the outer surface with an associated convection coefficient of H naught 11,000 watt per meter square Kelvin. So the steam condenses on the outer surface of the tubes. So steam is condensing in the shell. Steam is condensing in the shell on the surface of the tubes. Okay, and their convection coefficient is given. So convection coefficient for the condensation is given. That's the outside. The heat transfer rate that must be affected by the heat exchanger is this. So heat transfer rate is given. That means how much is the total amount of heat that will be transferred during this process of condensation is given. It's 2 into 10 power 9 watt. 2 is what? It's gigawatt. Right? And this is accomplished by passing cooling water through the tubes at a rate of 3 into 10 power 4 kg per second. So inside the tubes you have cooling water. So for condensation you need to reject heat, and that heat is rejected being supplied to the cooling water. So the cooling water takes in the heat of condensation. Okay. And the cooling water enters the tubes at 3 into 10 power 4 kg per second. This is the mass flow rate of the cooling water, overall mass flow rate of the cooling water. Okay. The water enters at 20 degrees centigrade. So the cooling water enters at 20 degrees centigrade, while the steam condenses at 50 degrees centigrade. So water will enter at 20 degree, cooling water enters at 20 degree, and then its temperature will keep on rising, but will never rise above 50. Okay, and 50 is the temperature at which condensation is occurring of the steam. What is the temperature of the cooling water emerging from the condenser? I mean at the exit, what is the temperature of the cooling water? what is the required tube length per pass? Tube length per pass means the length of the shell, because there are 2 passes here. So length of the shell actually, which is asked. L. L is the length of the shell. So that means one tube has the total length 2L. L for one pass, L again for another pass.
For every pass there is L. So
Yes, for every pass there is L. Okay. So what is the required tube length per pass? So basically we want to know the length. So that means if we want to know the length, so heat exchanger area is not given, right? So this is kind of a design problem. We had 2 kind of problems: design problem and performance problems. In the performance problem, area is given and inlets are given, you need to find the outlets. Here, area is not given, you wanted to find area. So that means it's kind of a design problem. Okay. Anyways, we will use since we are studying the NTU effectiveness method, so we are going to use that method, NTU effectiveness method. The very first thing is to draw the temperature profile. Now this is a shell and tube heat exchanger. So other than that, if you have just a parallel flow, then your temperature profile will be different. In all other cases, you will draw it as a counterflow. So here, for the case of hot fluid, its temperature would be, okay, the steam that is condensing, is it hot fluid or cold fluid? Hot. Why? Because it is rejecting heat. It is supplying heat. So the hot one supplies the heat. Okay, that's why it is hot. Okay, so it is a hot fluid and its temperature would remain constant throughout. It's 50 degree T hot inlet, 50 degree T hot outlet. Okay. However, the cooling water, its temperature will increase, but we will model we will draw it as a counterflow. Okay, so it enters from here, exits here. Although this is not counterflow, since there are 2 passes, so half of the length is parallel flow, other half of the length is counterflow. But anyways, we are going to represent it here as counterflow. For all the cases, if it is a cross flow, if it is shell and tube heat exchanger, multiple passes, you draw it as a counterflow. Only if it is just the parallel flow, then you draw it as parallel flow. Otherwise, representatively, you draw it as a counterflow. Okay. So T cold inlet enters at 20 degree. We don't know what is the exit. This is actually one of the things we need to find. T cold outlet. Okay. Mass flow rate of, so mass flow rates are given, right?
Yes.
No, mass flow rate of only the cooling water through the tubes, that is given. Okay. Cooling water through the tubes is given. But what is the mass flow rate in the shell? That's not given. Okay. So this is the problem. Now we have NTU is equals to UA over C minimum. Okay. And we have effectiveness. Now this is the case where we want to find area. This is the case where we want to find the area. Why? Because we don't know the length. We want to find the length. Length will come in area, in the formula of area, of heat transfer area. So we need to find area. But if we want to find area, first we should know what is U, what is C minimum, what is NTU. U is given. Okay, no, U is also not given. We will calculate U. Only H outer side is given. Okay. And if we know U, C minimum and NTU, then we can find what is area. But in order to find NTU, now how would we find NTU? In order to find NTU, since this is a single shell, 2 tube passes, shell and tube heat exchanger. Okay, so we can use the correlation there between NTU and effectiveness, or we can use the graph. Both of them are okay, we can use them. So, but that correlation or graph would need effectiveness, okay, effectiveness and CR. CR is C minimum divided by C maximum, right? So if we know effectiveness and CR, then we can find NTU. If we know NTU, we calculate U, and C minimum, we'll find area. If we know area, we'll find the length. So you're getting the sequence through which we are solving the problem? Okay, now for finding effectiveness, what is effectiveness? Effectiveness is Q upon Q max. Effectiveness is Q upon Q max.
We have formula for Q max.
Now, for Q will be same for the hot fluid as well as for the cold fluid. But for the hot fluid, we don't have the mass flow rate. Okay, and for the cold fluid, yeah, Q is given. This is one important point.
Q max.
We need Q max. So Q is given. Sorry. Q is given. That's good. But we need Q max. But for finding Q max, it's Q max is equals to C minimum multiplied by T hot inlet minus T cold inlet, right? So Q max is C minimum multiplied by T hot inlet minus T cold inlet. Now T hot inlet is also given, T cold inlet is also given, C minimum. What do you think about C minimum? Is it given?
No, we have to calculate.
You have to calculate C minimum. How do you calculate C minimum?
We calculate for hot and cold.
Okay, that's good. But there is one thing, as I told you, that C for the case of evaporation or condensation goes to infinity. So for this case, C is infinity.
So
Already the minimum case is this case. That's what we know. If it is condensation or evaporation, C for that case is infinity. So C minimum becomes the other case, right? So we can use that. The other thing we wanted to find out, what is the cooling water, what is the temperature of the cooling water emerging out of the condenser? We needed to find out TC out. How can we find TC out? We have the formula Q is equals to m dot Cp delta T, right? You can use that formula because Q is known. Q is known, 2 into 10 to the power 9 watt, and mass flow rate of the cold fluid is known, right? Because this is my cold fluid, and this mass flow rate is given. Okay, so mass flow rate of the cold fluid is known, and Cp. How we find Cp? For finding Cp, we should know the cold inlet and outlet temperature, but we know only the inlet temperature.
But we know that
we know
that the
between
out
20 and 50.
didn't exceed 50.
Yes. So now we know that. So anyways, here assumption comes. You will assume a value, but your assumption should be between the realistic ranges.
50 and 20.
Yes. So here they took the assumption as TC mean comes out 27. That means that they assume TC out as
27.
30, 34.
TC.
20 to 34 will give a mean of 27.
And average.
Average.
I assume
Can-
the TC out or the
TC out بعدين تاخد الافريج بين الاوت والان.
So you
50?
you can assume. No, it should be less than 50. Because TC out can never reach 50.
49.
49, خلاص. Even if you take 49, I cannot make it wrong. Your assumption is within the valid range, but you have to tell after that the problem needs iteration. Problem needs to be resolved again, although you will not be solving it again. You will be solving it one time. Okay? Because you see, suppose you take TC out as 49, okay, then your T average will be how much? 20 to 49,
20, 50, 70,
approximately 35.
35,
Okay.
34.
So you will use 35 degree here to find out the properties of water, and then you're going to substitute the CP value at 35 degree, and you will get TC out from here. And once you get TC out, you will realize that TC out is quite different from what you assumed. So you will not be solving it again, but you will just write a statement that since TC out is far off from my assumption, so the problem needs iteration, needs to be resolved again, although you will not be solving it again. You have shown the procedure, it's good enough for me. Is okay? So here, since this is the book and they know the answers, so so they took an assumption, a very good and correct assumption of 27 degrees centigrade, and based on that assumption of T mean of the coal at 27 degrees, and based on that assumption they took out the properties of water. Okay?
But you can give us the temperature in the test or the exams.
No, I want to test you.
This is not assumption,
Okay. Is it clear so far? Is it clear so far?
Yes.
Okay, so now what we need to do, we need to find out the T cold outlet. This is one of the things that we needed to find, T cold outlet, okay? For T cold outlet, we'll use this formula. So Q is equals to m dot C Cp. Now we know Cp based on our assumption. We know what is Cp, and it will be T cold outlet minus T cold inlet. Right? That's the formula. We know T cold inlet. We will find what is T cold outlet. Is it clear? So that's done here. Found out T cold outlet, and look, their T cold outlet, 36 degrees centigrade, and their assumption was 34.
34.
Close enough. 2 degrees. Anyways, now the first part of the problem is done. That was the first part of the problem, was what is the temperature of the cooling water emerging from the condenser. The second part of the problem was finding the length, and for that we know that we have to use this NTU calculation. If you know NTU, use C minimum, you can find out. Okay, now we can find C minimum. Okay,
Yes.
C minimum is what? C minimum is, since the hot side is the side where condensation is occurring, so that is maximum. So the cold side will be the one which is C minimum. So it will be m dot C, which you already know, multiply by CPC, which you already know. Okay? So that's your C minimum. So now you know C minimum. If you know U and NTU, you can find what is A. And if you know A, you can find what is the length here. Okay?
NTU from the
First of all, okay, let's first of all talk about U. How would we find U?
we need to find the edge for the cold fluid.
Yeah, because it's a thin wall tube, so there is no wall thickness, conductive resistance. There is no conductive resistance. So your U will be 1 upon 1 by Hi plus 1 by H naught. As simple as that. Okay, that will be your U. Now H naught, outside heat transfer coefficient, is given, but Hi inside the tube, that is not given. So move back to chapter number 8.
Correlations.
Correlation, obviously. How would find H? Okay, So you have to move back to chapter number 8 and find out correlation from there. But first thing, you need to find out whether it is laminar or turbulent. So how do you find that? By using the Reynolds number. So Reynolds number is what?
Rho VL.
Okay. Tell me in terms of the mass flow rate, m dot.
In terms of mass flow rate.
Mass flow rate to volume.
4m dot.
4m dot upon pi d mu. It's good? So you saw the lectures?
Yes, with
Anyways, it's still a clever thing. So 4m dot upon pi d mu. Now mu is a property that you already know. Mu is a property that you already know. Diameter you know. Pi you know. 4 you know. Let's talk about m dot.
For the cold fluid.
Yeah, for the cold fluid.
Given
Ah, big mistake.
in the cold. And
Yeah,
also the
that's
cold.
true.
this is the total mass flow.
Ah, yes. You want to find out the Reynolds number in a tube. That's how you find out whether the flow inside tube is laminar or turbulent, right? So this is the total mass flow rate of the cold fluid in all the tubes. How many tubes we have? We have 2 tube passes,
60.
but the bunch of tubes which are going to make 2 tube passes, how many tubes are there in that bunch of tubes? 30,000 tubes. So it's a very big heat exchanger. It's like the size of the building. 30,000 tubes are passing and then returning back. Okay? So we have to divide the overall mass flow rate of the cold fluid by 30,000. So mass flow rate of the cold fluid is how much?
30,
Into?
30,000.
It's also 30,000.
So 1,000.
1. Yeah, 1,000 gram per second you can say. 1 kg. Is it clear? So mass flow rate here is 30,000 divided by 30,000, which will be 1 kg per second. So now we determine the mass flow rate 4m dot upon pi du. That's how 1 comes here. Okay, 1 kg per second. And the Reynolds number comes out to be 59,567. What do you think? Laminar or turbulent? Turbulent. Because the criteria is if above 10,000, it's surely be turbulent for the tube. Okay. Between 2,000 to 10,000, it's transition, a combination of laminar and turbulent. Less than 2,000, it's laminar. Okay. Above 10,000, surely turbulent. Now we know it is turbulent, and we know what is the Prandtl number. So then there are 3 equations there in chapter number 8, and based on which you will decide which one to use. So basically it will be the Dittus-Boiter equation that you will be using. 0.023 Reynolds number power 4 by 5, Prandtl number power n, where n was 0.3 or 0.4, based upon if it is cooling or if it is heating. Okay, based upon if Ts is greater than Tm or Ts is less than Tm. Okay, so in this case, since the water is being heated and Ts is more, Tm is less. Tm is the mean temperature of the fluid inside the tube. That is less. Yes. So we have 0.4 here. Substitute all the values here. It comes out that the Nusselt number is 308. Then substitute the formula of Nusselt number. You'll find that Hi is 7543. Substitute the value of Hi here. You'll find what is U. Is it clear? So now you know Hi. You'll find U. Once you know U, now you know U. You know C minimum. Okay. If you know NTU, you can find what is A.
From the effectiveness we can find.
So now you need to know effectiveness and CR in order to find NTU. Now you need to know effectiveness and CR in order to find NTU. Now effectiveness is Q upon Q max. Q is something you already know. What is Q max? Q max is C minimum, which you already know, into THI, which you already know, into minus TCI, which you already know. So you know all the parameters in order to find Q max. So now you know Q max. Based on that, you will find what is effectiveness. You know what will be the CR in this case? C minimum over C maximum, where C maximum approaches infinity, so it's 0. Okay? For the CR0, you have that formula. For CR0. So this is to find effectiveness. The other one is, this one. That is for CR0. NTU equals to negative ln 1 minus effectiveness. You know effectiveness, and that's it. Nothing else is needed.
So here I can't use the graphs. I cannot use the graphs here.
No, you cannot use the graph here. Okay. Yeah, you can use the graph as well. I'm sorry about that. See, in the graph, this is parallel flow, that is counter flow. This is shell and tube heat exchanger, right? And for C min by C max equals to 0. That's the very first curve. Okay. So based on your effectiveness, you will find what is NTU. So you can use the graph as well. You can use the equation. But here the equation is very simple and will give you most accurate answer. Okay.
Sir,
Yes?
what is the difference between the efficiency and the effectiveness?
Efficiency and effectiveness, it's a conceptual difference. Effectiveness is output over input. Sorry, efficiency is output over input. But here in heat exchangers, we don't have any output, we don't have any input. Well, I mean, they are same. Output and input are heat. And they are same. The amount of heat out is equals to the amount of heat in. So what? Efficiency is always 100%? Then sometimes we do not define efficiency, we define effectiveness. Effectiveness is what? It's kind of a relative term. How well the heat exchanger is performing compared to the what was the maximum possible performance of the heat exchanger. Okay, so it's like relative grading. Okay, you get that much percentage marks. Okay, how do we know it's good or bad? So compared to the others,
Yes.
or compared to the maximum.
Top 3.
So if let's say you have a son and your son comes and say, father, I got 90% marks. So your first question to check whether your son performed well or not, that what was the highest mark, right? And if your son say 100, I say, it's not really that good. Okay. So, yeah, but let's say your son come and say, father, I got 50% marks. So they say, okay, what was the maximum? Say, for father, 51 was the maximum. Okay, that's great. Anyways, this is effectiveness. This is effectiveness. You got the idea?
Yes.
Okay. Okay. So we come back here. Now, once we know CR and once we know effectiveness, we can find out what is NTU. Now, if we know NTU, we will find what is area. Right? If we know NTU, we will find what is area. But still, problem is not yet solved because we need to find the length per pass. Okay.
It's not that the area.
Okay. So area is equals to what? Pi dl. But for one pipe, for one pipe,
30,000.
for one pipe, it will not be pi dl, because one pipe length is not L. One pipe length is 2L, because we defined L as just one pass length. So one pipe is making 2 passes. So for one pipe, the total length is not L, it's 2L, where we define L as one pass.
What about the UCL?
Hmm?
This part. Have L. This part.
Normally what we do is that we assume that it's covered in it. So it's like this. It is from here to here. So your L is this. Yeah, there will be a little error. There will be a little error. So this is your L, and this is your so instead of having this part where you should have a straight line, you have a slight curve. So yeah, there is a little error. But anyways, this is good enough for our calculation. So is it clear? So for one pipe, it will be pi d 2L. That's the one pipe area. And how many pipes do you have? 30,000. So multiply by n. Let's say the number of pipes. So we know n, we know what is pi, we know d, we know what is area. We can find what is L, which will be the length of per pass.
You know the area?
It's clear? So that's how we solved this problem using NTU effectiveness analysis. Is there anything which you did not understand in the solution of the problem? Abdul Malik? Clear? Brade?
Yes, clear.
What's clear?
Review the lecture.
Yeah, reviewing the lecture there, right. Good. You're not multitasking. Okay, so that's how we solve this problem, and the per pass length comes out to be 4.51 meter. Okay, so that's the length of your shell and tube heat exchanger. Okay, that problem is over. Is there anything in that problem which you do not understand? So you are most welcome to ask. Okay, now let's move towards the last problem for this chapter and for convection as a whole. And this is kind of a big problem. So,
Every problem you say it's a very big problem. All the problems.
okay, we have a geothermal power plant. Geothermal power plant. You are studying geology, right?
Yeah.
Okay.
It's all about energy and
Really?
yes.
Oh, good. So we have we have geothermal power plant that utilizes pressurized deep groundwater at 147 degrees centigrade. Okay. When we say geothermal power plant, the only difference is that the source here in that it's using Rankine cycle, and Rankine cycle you are very aware of. Okay. So it has a boiler, and how you are providing supplying energy to the boiler, that is of your concern. So if you are supplying energy to the boiler by the hot water which is coming from the depth of the earth, so you know the core of the earth is very hot, and below, if you go to a certain level, you might be studying it.
Yes.
So there in geology. So there is very high temperatures available, high temperature water available, high pressure. So there is possibility to utilize that energy. Okay. So if we can push some water there, it will become very hot.
Can we come back?
Hmm?
Can we?
Yes.
There's courses in our program about geothermal power.
No, we don't have courses about geothermal power. We have course about renewable energy, and within the renewable energy, you will spend some time in discussing the geothermal energy, probably 1 week, but not too much, because it's not on the geothermal side much. It's more about the thermodynamic side still. Okay, geothermal side is what you study in geology. How much energy is there in the in the earth core? Anyways, so we have a geothermal power plant that utilizes pressurized deep groundwater, and see the temperature of the groundwater which is coming is 147 degrees centigrade. That is the temperature of the water coming from the ground. As the heat source for an organic Rankine cycle. Now this is an organic Rankine cycle. What's the difference between organic Rankine cycle and the regular Rankine cycle that you have studied? The only difference is that instead of using steam, they use some organic fluid.
Like?
I don't know what's like. So go to the chemistry. So some organic fluid. Okay? So it uses some organic fluid other than steam. But the processes, all the steps, everything is the same.
So just the fluid change.
Just the fluid change. Instead of steam, you have an organic fluid. Okay? So that is organic Rankine cycle. Okay? The operation of which is described further in comment 2. Okay? We are not discussing that. An evaporator consists of a vertically, now we have an evaporator. They call it evaporator, but it's actually boiler. So boiler and evaporator are almost the same thing. Okay? So boiler for the Rankine cycle. Okay? So you have an evaporator consisting of a vertically oriented shell and tube heat exchanger. So your boiler is basically a vertical shell and tube heat exchanger. Okay? With one shell pass and one tube pass. It has one shell pass and one tube pass. Transfers heat between tube side groundwater. So groundwater which is coming from the earth, it's in the tube. It's in the tube side. Okay? And the counterflow shell side organic fluid of the power cycle. So on the shell side, you have the organic fluid which enters. That organic fluid boils. In the tube side, you have the groundwater that flows counterflow. So if it is vertical, so shell side fluid is moving up, ground side fluid is moving down. But ground side fluid is inside the tube, shell side fluid is inside the shell. And inside the shell, while it is moving up, it also boils and comes out as gas. It's clear? The organic fluid enters the shell side of the evaporator as subcooled liquid. So it enters as subcooled liquid. So that means its temperature is not the saturation temperature. Its temperature is below saturation temperature. Okay, at 27 degrees centigrade. So T cold inlet is 27 degrees centigrade. Okay, once again, which is the cold fluid and which is the hot fluid? You have one fluid which is rejecting heat, other fluid accepting heat. Okay, so the one which is accepting heat is boiling. So which is the hot fluid here? Ground or the organic fluid?
Ground.
Ground is the hot fluid and organic is the cold fluid. So the organic fluid enters at 27 degrees centigrade. But this is not the saturation temperature. This is not the temperature at which boiling starts. Okay, because it enters subcooled and exits the evaporator as saturated vapor of quality 1. That's saturated, perfectly saturated vapor. It exits as that at temperature 122. So from 27 to 122, it remains liquid. Then at 122, boiling starts, and then the boiling finishes when everything is converted into vapor.
So everything happens in the.
Everything happens in this heat exchanger, vertical heat exchanger, shell and tube, from the bottom to the top.
I mean, heating is infinity.
We'll see. Because there are two parts. Boiling doesn't start initially. Initially, it is just the heating of the cold fluid from 27 to 122. After it reaches 122, as liquid, then boiling starts at the same temperature, then the temperature does not change. And so there is one part where the temperature is changing, there is another part where the temperature is not changing.
Air is like it, right? Air.
No, not air. The groundwater.
Ground, I mean, no air.
You will see.
You'll find.
Okay. Within the evaporator, heat transfer occurs between groundwater and organic fluid in stage A with UA this, and between liquid and groundwater and boiling organic fluid in stage B with UB this. So basically, now this is the figure. This is the figure. So this is your vertical shell and tube heat exchanger. This is your vertical shell and tube heat exchanger. From the geothermal source, that means from the ground, very hot water at 147 degrees centigrade enters this into the tubes, then goes, its temperature keep on dropping until it exits out of the shell and tube heat exchanger. Go back into the geothermal source. Okay. On the shell side, now we have here, this is the Rankine cycle. Okay, so in the Rankine cycle you have the boiler, after that you have the condenser, after that, this is your boiler. This is your boiler. So you have boiler, after that you have the turbine, then you have the condenser, then you have the pump, then again boiler. So that's, so this is your Rankine cycle, organic Rankine cycle. The difference is that here you don't have steam, you have the Rankine fluid, organic fluid. Sorry. So it enters at 27 degrees centigrade as subcooled liquid, then it passes, so here it mentions this is the liquid region in stage A. So from here at entering point until this point, there is no boiling. It's just temperature rise from 27 to 122. After it reaches this point, now the temperature is 122 and the boiling starts. Okay, now the temperature remains 122 throughout the upper section. And this upper region is a two-phase region where initially you have liquid and vapor, and then the vapor content keep on increasing and until you have here completely vapor exiting out. Okay. So this, you cannot assume this with the pool boiling. This is not pool boiling. You studied the pool boiling before in chapter. Pool boiling is a kind of a boiling where the liquid is stationary. Here the liquid is in motion. So that's flow boiling regimes. You did not study the flow boiling regimes. Okay? But you can study that. Nobody is stopping you.
Maybe in summer.
Okay. Is it clear? So you have this region where it's, okay, first of all, this is counterflow. In any case, it is counterflow. In this region, it is counterflow, but all liquid. So your organic fluid is also liquid, and your groundwater is liquid as it is. But here, when it starts into the stage B, in this region, the groundwater is liquid, but organic fluid starts boiling. So boiling is occurring in stage B. In stage A, there is no boiling. Okay, and then it exits as 122 degrees centigrade. Okay. Do you understand the process here? What's happening?
Yes.
Okay, we have not yet read the question totally. We're just understanding the process. Okay. Now read the question totally. Within the evaporator, heat transfer occurs between liquid groundwater and the organic fluid in stage A with UA this, so UA is given in this stage, and between liquid groundwater and boiling organic fluid in stage B. So in stage B you have boiling, in stage A you don't have boiling, and UB for this is also given. For groundwater and organic fluid, flow rates of mass flow rate of groundwater is given, and mass flow rate of our Rankine fluid, organic Rankine fluid, is also given. Determine the required evaporator heat transfer surface area. So what is the total heat transfer surface area? A is needed. Okay. The specific heat of the liquid organic fluid for the Rankine cycle, Cp is given, and its latent heat of vaporization, HFG, is given. First of all, what kind of problem is it? Is it a design problem or is it a performance calculation problem?
Design.
Why?
Area.
Because area is needed. In the performance calculation problem, area would be provided. Is this clear? So we need area. But we have now a combination of two heat exchangers in one, because two different processes. In one part you have boiling occurring, another part there is no boiling occurring. Okay. So now let's draw it here like this. So this is my shell and tube heat exchanger. Okay. Where the hot fluid enters here. Okay, let's first divide it into two parts as the book has divided. This is stage A, this is stage B. This is B, this is A. Okay, boiling occurs, saturation temperature is 122. So boiling occurs from in this region, and in this region temperature will not change when boiling is occurring.
Okay.
As you have studied this in thermodynamics.
Yes.
Okay. So far, are you guys with me or not? Is there anything that you do not understand? Good? Brade? Moment? Is there anything that you do not understand? Okay, khalas. Let's continue forward. Okay. Now we need to find out the area. Since we are considering it as two separate heat exchangers, so it will be, we find area for this separately, find area for this separately, add it together. That will be the total area. So area will be area of A plus area of B. Right? Now if you want to know area, what is the thing that you should know? Then you can find area.
NTU.
Good. So NTU is equals to UA upon C minimum. If you know what is NTU, you can find what is area.
U is given, C minimum.
Now U, if you see here, U is given for both the sides. U for A section is given, U for B section is given.
Yes.
Right? So you will have here, this is all for A, and then as you will have another NTU equals to UA upon C minimum. This is all for B. In both the cases, U are given. Is okay? You can find A if you know C minimum and NTU. If you can find A if you know C minimum and NTU. Okay?
CBR is given. CBR is given.
CPR is given. CPR is for what? It's for the refrigerant. Sorry, it's for the Rankine fluid, organic Rankine fluid. Okay. Okay, now let's try to follow up with this problem. The first thing is that we have some missing temperatures here. Let's try to find out the missing temperatures. We know TCO, we know this temperature here, we know this temperature here, but T hot out is not there, and T hot out at A is not there, T hot out at B is not there.
These two temperatures should be 122 also.
No, these two are the hot fluid temperatures. This is the cold fluid temperature. The hot fluid temperature is not known here.
From geothermal.
Yes. And the hot fluid outlet here is also not known. Now we need to find out what is the, okay, for the cold fluid side. For the cold fluid side, we can find out what is the total energy. We can find out what is the energy QB we can find out what is the energy QA. How? For the case of QA, it will be what? It will be m dot cold Cp is R delta T. Hello? वालेकुम सलाम। नहीं अभी क्लास चल रही है। हाँ चलो सही मानो।
मैं कह रही थी अली को ले जाओ तो जब तक माशाल्लाह थोड़ा फ्रेश हुआ मैं भी इसको थोड़ा सा काउंटिंग हो जाती है हमारे साथ मसले को ले जाने वाले हैं उसका।
अच्छा चलो सही है, फिर मैं क्लास के बाद बात करता हूँ। ओके
हाँ बच्चा बोल रहा है उसका स्कूल से निकल गया।
Okay, now let's come back to the problem. So, how will we find QA? QA will be mass flow rate of the cold fluid. Do we know the mass flow rate of the cold fluid? Mass flow rate of R will be same. So, mass flow rate of the organic Rankine fluid will be same throughout. So, we know what is mass flow rate of R. Is it clear? R is organic Rankine fluid, which is the cold fluid here. So we know the mass flow rate of the cold fluid, we know what is Cp, and we know what is delta T in this section. So it will be T cold out A minus T cold in A. That's this section. Okay? That's section A. So we know what is T cold out A, we know what is T cold in A. And we know what is the mass flow rate, we know what is Cp. So if we know all these terms, we can find what is QA. Is it clear? Now tell me about QB. Which formula will you use? M dot Cp delta T?
You don't have delta T.
They don't have delta T because T cold inlet for B is the same as T cold outlet for B because evaporation is going on. Do I need to say anything? Why you guys test my patience? Okay. So for QB, we cannot use m dot C delta T. We have m dot, but what's happening? It's the boiling which is occurring. And when boiling or condensation is occurring, then we can use the enthalpy. We don't need to go to the enthalpy chart. Latent heat of vaporization is given HFG from fluid to gas. Is it clear? So HFG is given. So it's not m dot C delta T because C delta T now is HFG.
Yes.
That's so we have m dot C will be there as it is, but not Cp delta T because there is no delta T. It's the boiling which is occurring. And in boiling, what's happening is that the liquid is being converted to vapor. So we need the enthalpy for this conversion. And that is given. Latent heat of vaporization, HFG, is 110 kilojoule per kg. Okay. So I will use here m dot C HFG.
It can be not given and left in the table.
No,
Has to be given.
has to be given. Is it clear? So HFG is given, m dot C is given, you can find what is QB, right? And if you know what is QB, so now you know the total Q as well. Is there anything that you, it's same, same. Because the same mass flow rate which enters here passes through this part of the heat exchanger, then enters into this part of the heat exchanger and exits. Only the thing is that its nature changed. It was liquid, now it is vapor, but the mass flow rate is same. Is clear? So we know what is QA, we know what is QB. Based on QA and QB, we can actually find what is the T hot outlet and what is the T hot outlet here. Let's say we want to find T hot outlet B. How can we find that?
It's equal to T hot inlet for A.
Okay. Yeah, it is equal to T hot inlet for A.
M dot C T inlet T outlet minus T inlet. For
Exactly, exactly. So we have this QB okay. QB is equals to M dot, now the hot fluid C T hot inlet B minus T hot outlet A. Oh, mashallah, so much incoming now. Okay. So you see here, QB is given, mass flow rate hot fluid is given, mass of the groundwater. Your hot fluid is the groundwater. And TB inlet is given. TB,
So why of A, not B?
oh sorry, this is for
B. B. Okay.
make sense?
Yes.
Okay. So TH not B is something that you need to find. What about CP?
Property. It's a property.
Again here you need an assumption because you need to take the mean between the two temperatures. Now here what they took is that they did not take the mean of these two temperatures, they took the mean of the whole system.
hot in minus cold out.
So T hot in B minus or T hot plus T hot out A. So they take one CP value for the whole average, okay? And again for that average there needs to be an assumption because you also don't know this, okay? So they took the assumption as T temperature taken at 405 Kelvin. It was 147, okay? So they took it at around 15 degree. So they assumed that the temperature drop will be around 30 degree overall. So 15 degree drop will be around 405 Kelvin.
And between 147 and 127?
No, between 147 and the outlet.
And he assumed the outlet will be what?
He assumed the outlet will be 30 degree less than the inlet. Okay. Anyways, I told you about the assumption. Okay.
But now how can I know?
Yes. Two assumptions. Now it's the same.
What is the restriction?
It's again.
I should assume between what values?
Now in this case, you have one value. It should not be. So your outlet must not reach 27.
Okay.
The temperature will drop, but it cannot drop below 27, right? So suppose you take it at 28. Okay, so that's good enough. But what they took is that they took 147 to 30 degree less will be 117. 117. So they assume that the outlet is at 117. So the average will be in between, and that will be approximately 405 Kelvin. Okay. Again, this is an assumption. If you make a different assumption, it's okay.
Can be given. Can be given.
No, I want you to test it. Okay. So now the only thing for you is that your value of T hot outlet, it must not be 147. Your value of T hot outlet, it must not be 147, and it must not be 27. It must be in between the two. If it is in between the two, then reasonable. Is it clear?
Yes.
So now you know CP. Based on that CP, you will find out what is T hot outlet B. Okay. So So now we know THOB, THIA, because these two are same. Okay, we need to find T hot outlet A. Can somebody tell me how can we find that? There are two ways. Either you consider this as a whole heat exchanger and use the total Q, or you can use QA. Both are okay. The better option will be to use this as a whole.
Why?
Because you're using C minimum, C mean for the whole, and you know that this temperature is correct. This temperature might be wrong because of your assumption here. It's clear? So chances of error are less if you use the exact values. Okay? So here what they did in the book as well, and it's also logical. The main logic is that what they did is that they said total heat QA plus QB is equals to m dot h Cp delta T, T hot inlet B minus T hot outlet A.
So we have m dot, we have CP.
Why m dot for H?
Because we are finding for the hot side. Okay, Q will be the same for hot and cold. Okay, so m dot h we know, QA QB we know, these are all the exact values we know. T hot inlet B, this is also the exact value we know. Okay, Cp is our assumption, and they took the assumption already at the mean of the whole heat exchanger, combination of two. Okay, so this will be more accurate compared to if you just use QB. If you just use QB, I cannot do it wrong in the exam. Let's say if you just use QB. So if you just use QB, what will be the formula? QB will be m dot h Cp T hot outlet B minus T hot outlet A. Right? T hot outlet B equals to T hot inlet A. So we know this thing, and we know Cp, we know m dot h, we know QB. You can find T hot inlet A. But in this case, there is chances of error in THOB. So there will be chances of more error in THOA. Error will be accumulated if you are already using an error value. But in this case, this is not an error value. This was an input from the question. So there is no accumulation of error. But anyways, if you use like this or if you use like this, both are okay. Is it clear or not? Is there anything which is not clear in this step? Okay, I write here T hot in A minus T hot out A. Make sense? Because the two are same. Is it clear? Is there anything so far which is not clear?
The difference between these two formulas is, in the second formula, that Cv is exactly known.
No, Cp we use the same value. Yes, we use the average value of the whole heat exchanger.
This is in the A and plus B.
Yes.
But in B,
In B, the Cp will still be the same, whatever we assumed for calculating this. Okay, but only the thing is that this value might have error in it, because it was calculated using the first calculation, and even in our first calculation, because of our Cp, there might be certain error. So you are using an error value to calculate another value. More error. Here, no error value here. So less error chances here.
this is THIA.
THI.
Inlet of A and
No,
outlet
no.
of A.
THIA minus THOA. That's correct. This is between this. And THIB minus THOA for the whole. That's for this. Okay. So either you can use this or you can use this. We are finding this.
QB,
No,
you said when you find QB, you did HIA minus HOA. QP.
QB, yes.
In region
I-
B, I will calculate the temperature, difference temperature between A and
Yeah. Oh, okay. Sorry, this is not QB. This is QA. Correct.
because there is HV.
Yeah.
So,
That's fine. This is A. I'm sorry.
when in the Q in region A, I all the things in A.
A, exactly. Is it clear so far? Is there anything that is not clear? This is a difficult problem, but I'm moving slowly so that you understand. Okay. So we found all the Q's and now we found all the temperatures. So all the temperatures here are now known. Okay. Since we know all the temperatures, now what was required? The required was we need to find out, we know what is U, if we can find NTU and C minimum. If we find NTU and C minimum, we can find out what is area. Okay. Now C minimum will be what? Okay, let's talk about section A. For section A, C minimum will be what? Now in section A, both are liquid. Your Rankine fluid is also liquid and your hot fluid, groundwater fluid is also liquid. So you have to calculate C for hot side as well as for cold side and then see which one is the minimum. Okay, so C for hot side will be what? M dot C into CPC. C for M dot H to CPH. C for cold side will be M dot C CPC. We know what is CPH, hot side, we took it from the tables. We know what is CPC given in the problem. Okay. We know what is M dot H, we know what is M dot C.
So we can find both CH and C.
So we can find both CH and CC. Okay. And based on that, we will decide which one is the C minimum.
The below.
The lower value is C minimum. Okay. So now we know what is C minimum here. Is it clear?
Yeah.
For the other case, for section B, the one which is evaporating will be maximum.
Much higher, of course.
Okay. So the other one will be
Minimum.
minimum. So it will be C minimum will be C dot. So evaporating one is the cold side, right? The cold side is the one which is evaporating in section B. So the hot side will be your C minimum. So it will be M dot H CP H. Is it clear?
Again.
In section B, you have a hot fluid and a cold fluid. The hot fluid is the one which is the groundwater, and the cold fluid is the one which is the Rankine fluid, which is evaporating. Since this is evaporating, so capital C for cold will be maximum. Since this is evaporating, so capital C for cold will be maximum. So C minimum in this case will be for the hot fluid. So M dot H CPH. Is it clear?
So, okay, the value for the CH here, so you're going to equal the CH there?
No. So the both will be same values here, CH. But here C minimum will be based on the decision of between this and this. Here C minimum, it's already pre-decided.
Okay.
It's the hot side. Okay.
CBH and CB cold.
So look at here. We have CH for the hot side, CC for the cold side. It's 42670 6760. Okay. So
Both CBG and CBR is given?
CPG and CPR, oh yeah,
Okay.
one is given, other you find from the table after making assumption for the hot side.
Which is for the hot side?
This is for the hot side. Cold side it was given. Okay. So if you see here, CH and CC are this. So in section A, which one will be minimum? CC or CH?
CC.
CC will be minimum. So here C minimum will be CC. In section B, it's not a matter of question, pre-decided that this is C minimum. Is clear? So now we decided what is C minimum here. We know what is decided what is C minimum here. Okay. What will be CR here? Now we need to know NTU. For NTU we need two things, effectiveness and CR. For NTU we need two things, effectiveness and CR. Okay. So we need effectiveness here, we need CR here. We need effectiveness here, we need CR here. What about CR here, section B? It will be 0 because CR is C min over C max, where C max here approaches infinity, so CR will be 0. Okay, and if it is 0, then you know which formula you have to use. Okay, let's discuss about here. Here it will be C min over C max, but you know what is C min and you know what is C max. This is C min, this is C max. So this divided by this. So you know what is CR. Is it clear? Talk about effectiveness. Effectiveness is Q upon Q max. Right? Q upon Q max. Q upon Q max. So if it is for section A, so QA is known. QA is known, right? What about Q max?
The total?
C minimum.
Same.
No. It has a
C
lot.
minimum.
It has a lot.
So Q max, I should, right, okay, Q max. Q max is equals to C minimum into T hot inlet minus T cold inlet, if we are doing it for A, right? So C minimum for A is known, whatever. T hot inlet for A is this. T cold inlet for A is this. Is it clear? So based on that, you will find out what is Q max A. Similarly, you will have Q max B. It will be C minimum T hot inlet minus T cold inlet, right? So C minimum known. T hot inlet is this. T cold inlet is this. Is it clear? So now you know this, so you know what is Q max. So now you know Q max for, so here also Q upon Q max. So you know Q, you know Q max, you know Q max, so you will know what is the effectiveness here, you know what is the effectiveness here.
There is overall between B and A.
No, there is no overall, because we are solving at two different sections as two different heat exchangers, because on one side there is evaporation, other side there is no evaporation. You have to solve it separately. Is it clear that now you know effectiveness for both the problem? Now if you know effectiveness and if you know CR,
You can find NTU.
you can find NTU for both cases. But for this case, NTU is simple by that equation which we saw before as well. In this case, what kind of flow is it? It's a counterflow heat exchanger. So your NTU will be, because in this case there is no evaporation or condensation. So it's just counterflow heat exchanger. So your hot fluid is moving down, your cold is moving up. Okay? So for counterflow heat exchanger, okay, NTU for counterflow heat exchanger. Okay?
I suggest to go to the graph.
So you can use this, you can use this. Okay. CR, is CR equals to 1 or CR less than 1? It's less than 1. Less than 1. So you will use this formula. Is it clear? So now you know the NTU here, you know the NTU here. Once you know NTU, U, C minimum, NTU, U, C minimum, you will find area here, you will find area here. Substitute the two areas, add them together, that's it. Your answer is in meter square.
We finish.
Problem solved.
How about it? It's a story, not a problem.
This problem was heavy. But is there anything in the problem that you did not understand?
No.
I moved slowly
Yes.
so that you understand each and every step.
There is another homework question like this. Two section.
So Alhamdulillah, your convection is over.
Alhamdulillah.
Now the thing is that in the conduction, the most difficult chapter was chapter number 3.
Fence.
In convection, the most difficult chapter is chapter number 11. And none of them will be eliminated in the final.
Awesome.
So they will be there in the final. 3 and 11 cannot compromise over them.
3 and 11 and plus the chapter.
We will discuss inshallah.
We'll discuss.
Not
Okay.
final word. inshallah.
Don't make the final right now.
Okay. So that's it. We are done.
You already did.
No, not yet.